All right, let's talk running economy. This is part 2 of chapter 2 of Tim Noakes, The Law of Running. Running economy is a really important parameter to understand. And let's go through it. So VO2 max, we already established via part 1 that by itself is not a good predictor of endurance performance. Running economy, however, may be a good predictor of performance. What is running economy? It's the amount of oxygen, the rate of oxygen used when running at a constant submaximal running speed. So it's a rate of oxygen consumption for a given speed, mLs per kg per minute, liters per minute, either way. It's for a specific speed. Okay, let's go through it. The amount of oxygen consumption for a given speed, and clearly we have runners that are either economical, like Steve Prefontaine, or uneconomical, like Weird Al Yankovic running with scissors. Obviously, running style influences running economy, how effective someone is at using oxygen for a given speed. And we can look at a good runner versus a novice runner, and we can detect their movements are quite different to even just the eye. And some people just look like good runners because they're being more economical in their movements. So let's look at some data. This is in chapter 2, figure 2.9. This is an important figure to understand. On the y-axis is rate of oxygen consumption, mLs of oxygen per kilogram body mass per minute. And again, you may be familiar with saying mLs per minute per kg. Either way is fine. On the x-axis is running speed in kilometers per hour. And we've got 3 runners: runner A, runner B, and runner C. And these are VO2 data of these mythical runners. So doing a graded exercise test from 15 to 20 miles per hour, runner A stopped here. Runner B stopped the test at the same speed, and runner C went all the way over to 22.5 kilometers per hour. Again, these are hypothetical data. So here, if we look at running economy, which is a submaximal speed, running economy for runner C is better than runner A. And I say the word better. I don't say less or greater when I start using running economy, because it can get a little confusing in terms of comparing the magnitude of some numbers versus what the concept means. So here, even though Noakes uses A less than B less than C, conceptually, this running economy, this runner uses more oxygen, uses oxygen at a faster rate to achieve the same speed as B or C. So we would say the economy is less for runner A. Runner A would be less economical than runner C, but VO2, rate of oxygen consumption, is lower for C versus A. That defines running economy. And even out here, we look at the peak value that runners A and B achieved. They achieved the same peak velocity at the end of the test, but different VO2 maxes. That goes back to what we talked about in part 1 of this chapter, is that we have the same performance, but different VO2 maxes. Whereas runner C had the same VO2 max as B, but a much better running performance in terms of graded exercise test. They went all the way to 22.5 kilometers per hour. So same VO2 max, but better performance. All right, and that's just what this line is representing, is that if we look at for this rate of oxygen consumption, runner A is only going to run just over 18 kilometers per hour, but runner C is going to be able to run 21 kilometers per hour. Runner C is more economical than runner A. This is just another way to look at it. For given VO2, runner C is able to run faster, or for given speed, runner A needs more rate of oxygen consumption than runner C. Here's just some data from some different runners. and groups of line. One is children, two is Craig Virgin, and so forth with each runner. Um, on the y-axis, rate of oxygen consumption, and I want you to get in the habit of always looking at what's on the y-axis for these plots, because we need to be really careful in reading some of these plots. This is mLs per kg per minute, so this is rate of oxygen consumption, and on the x-axis is running speed. And we can see these runners are all different in terms of where they fall, not only the maximum speed, but where they are for any given speed. So if we look at 23 kilometers per hour, runner 9 used the least amount of oxygen consumption. Runner 2 is greatest, and even looking at children, they're really high. So children, in essence, for any of these speeds, were less economical than any of these runners. That makes sense. Maybe children just haven't learned the right movements to be economical, or maybe their bodies are built in a way at that age that requires more rate of oxygen consumption than adult runners. But what's interesting here is we see different slopes of these lines too. Okay, this is a steep slope. This is not as steep, a little subtle, but that's important. And we're going to need to talk about that. So these are some data and represent running economy for given speed looking vertically, okay? Or if we go horizontally for 60 mLs per kg per minute, kids can only run this fast, just to almost about 16 kilometers per hour, whereas runner 9 can be running over 21 kilometers per hour. That's fast, okay? That's fast. That's a half marathon in an hour. That's phenomenal. Okay, really, really fast. A lot of people, mere mortals, just want to get under 2 hours for a half marathon. All right, so now I'm going to introduce an entirely different but yet similar concept. So rather than running economy, I'm going to introduce this term energetic cost of locomotion. And this is going to be really important as we go forward. And we need to understand how energetic cost of locomotion is related to running economy, but yet different. All right, so energetic cost of locomotion is the amount of oxygen needed to cover a particular distance. And the units will be mLs per kg per kilometer. Okay, this denominator right here is distance instead of time. So rather than mLs per kg per minute, we're going to use mLs per kg per kilometer for energetic cost of locomotion. So it's a total amount of oxygen. It's as if you took all that oxygen and put it into a bag, and you said, this is how much oxygen was used to cover a distance. Whereas rate of oxygen consumption is how fast we're using oxygen. Okay, two different concepts, but mathematically related. And I want to go through that. So let's look at energetic cost of locomotion on the y-axis. So again, pay attention to what's on the y-axis and what the units are. And on the x-axis is speed. And I'm just going to show you some data modified from a couple of different studies. If we look at walking, this is what energetic cost of locomotion will look like for walking. What this means is if we walk really slow, to cover a certain distance, we need to consume a lot of oxygen. So let's say we're going to walk across campus, but we're going to go really, really slow. By the time we get across campus, we will have consumed a lot of oxygen. And likewise, if we go faster and we walk across campus really, really, really fast, like almost to the point, or maybe even faster than the speed that we want to start running at. Of course, we look silly, right? But we're going to be walking really, really fast. And we do that across campus, we're also going to consume a lot of oxygen to cover that distance, liters per oxygen, okay? There's a speed somewhere between going really, really slow and really, really fast walking. That's the minimum. Interestingly, when you walk across campus and you just sort of walk because you're just self-selecting a speed, you probably pick this speed that results in the least amount of oxygen consumed to cover that distance. That's actually really interesting. And that can be explained by some biomechanics in terms of how a pendulum swings. All right? We won't get into that here. but this minimum speed corresponds to some pretty neat physics. All right, so that's walking. Well, what happens with running? So let me go through this one more time. What we're doing here is we're looking at how much oxygen we're going to consume to cover a particular distance as we walk faster and faster and faster and faster. And walking is this complex curve where there's a minimum amount of oxygen that is consumed at a particular speed. So now let's continue this example, and we start deciding to run. And then we want to run faster, and then we want to run faster and run faster for a kilometer, or maybe a mile if we want to put it in that units. Well, interestingly, if we measure the amount of oxygen to cover that distance at any of these speeds, running is the same energetic cost of locomotion. That seems odd. But if we're going to run, let me talk through this a little bit. If we're going to run fast, we're going to be out here, we're going to cover that distance in a shorter period of time and therefore consume a lower amount of total oxygen. But if we're going to run slow, we're going to cover that distance over a longer period of time, but actually we're going to consume the same amount of oxygen. Okay, now, I'm talking about amount of oxygen per distance, not rate of oxygen consumption. As we're running faster, the rate of oxygen used is greater at the faster speeds than the slower speeds. Okay, the rate of oxygen consumption is greater, but the total amount of oxygen consumed over a distance is the same. You can think about this as a car. Let's say you're going to drive, 100 miles. That 100 miles will take you a certain amount of fuel. And this is sort of a bad example, but the concept is all right. If you drive that 100 miles at 50 miles versus 55 miles, your gas consumption will still be the same, but the rate of using the consumption is different. You still have to fill up with a certain amount of gallons to cover that distance in the car. All right, so now interestingly, the amount of oxygen used is directly related to calories. We'll get more into calories later on, especially in the thermoregulation chapter, but calories are just a unit of heat. And we know food has a certain amount of calories. If you eat a candy bar, 100 calories, 200 calories, whatever the candy bar is. The amount of oxygen used is going to be related to the amount of calories used as well. All right, so let's keep that in mind. Let me go on here. So in looking at these different runners, if we look at a more economical runner here versus a less economical runner here, what we're really saying is that the amount of oxygen used for that runner 9, is less for any speed than for other runners who are less economical. They're going to need less calories to cover a particular distance than other runners. All right, now let me explain this a little bit more. I'll explain some of the math behind it, because a lot of people get hung up on this idea that it's the same amount of oxygen regardless of speed for running. So let's look at the math of it. Here's some data from Falls and Humphreys. And these data are rate of oxygen consumption, liters per minute over running speed, meters per minute. All right, I'm using these units because I'm going to do some math here in just a second. If we look at walking and we look at the rate of oxygen consumption, it will follow this sort of curved path. And then for running, which is this part of the line here, it's a straight line. Oh, I should have explained what this means. So what happens is when we start doing this test, we will start off walking at a slow speed, and then we'll increment the speed. And at some point, we're going to want to transition from walking to running. That's going to occur somewhere around where these two lines cross. But to do this test, what I do is I tell the person, the subject, to continue to walk, even though they might want to run. they have to continue to walk until the point that they can no longer physically walk. That's where this line ends. Then I do the test again, but this time I tell the subject to, even though you may feel like you want to walk, I want you to run. So you're going to be running a really slow speed. You're going to feel awkward, okay? But we can start running slower and then increase in our running speed. These two lines intersect, okay, at some point, and we call this a transition point. We'll talk a little bit more about when someone does decide to transition from walk to run. Interestingly, it's not the speed that these two lines cross. We may actually start deciding to run sooner than that speed if we're going in an increasing manner of speed. But interestingly, if we're running and we start slowing the speed down, we may actually stop running sooner than we would need to transition to walk. So it's really, this preferred transition speed is a really interesting area of research in terms of why we transition from one gait to another, but it's not because of our rate of oxygen consumption. It's not where those two lines cross. Okay, so let's look at the math here. Well, what I'm going to tell you is that energetic cost of locomotion is the slope of the VO2 rate of oxygen consumption versus speed plot. Slope represents the steepness of the plot. And for those who've had biomechanics with me, and probably biomechanics with anyone else, you've probably gone through slope. Here, this is a steep slope. This is a less steep slope. This is a steep slope again. So let's just look at the math behind energetic cost of locomotion. Here's slope, is rise over run, change in y-axis over change in x-axis. That's the change in liters per minute over the change of meters per minute. It's just following our math. If we do our algebra, that actually cancels out to liters per minute. This is the oxygen consumed over a distance. That's energetic cost of locomotion. So the slope of the VO2, the rate of oxygen consumption versus speed plot, is energetic cost of locomotion. So if we look at this slope anywhere along here, the slope is the same, meaning that the energetic cost of locomotion will be the same. The slope here is steep, meaning energetic cost of locomotion is greater. The slope here is less steep. That's going to be lower energetic cost of locomotion. And here it's steep again. That's going to be a higher energetic cost of locomotion. So that corresponds exactly to our energetic cost of locomotion plot. Walking has a minimum and running is the same. I put running speed here. This should just be speed, but that's okay. The important things to know here is energetic cost of locomotion is liters of oxygen per distance. It's the amount of oxygen used to cover a particular distance. Now, there's some neat research out there that maybe this is not a straight line, and maybe a preferred pace is a subtle minimum that occurs in this. If that's the case, then this relationship between VO2 and speed is not linear, it has to be nonlinear. And it's sort of shaped like that at that point, right? So the math has to line up here. And again, people will sometimes it's hard to look at these data to say, oh, this is the amount of oxygen consumed is the same regardless of speed. Well, remember, the amount of oxygen consumed is going to be related to calories used. So let's look at some data from a textbook. So this is our Powers and Holly. This is walking. This is net caloric cost per mile of walking. So this is walking a mile, how many calories it costs to walk a mile or run a mile. Walking 2, 2.5, 3, 3.5, all the way up to 5 miles per hour. This is just different units for velocity. Here's the calories used per kilogram body weight, it really should be body mass, per mile. 0.77, 0.77, 0.96, 1.15, 1.3. More calories used to walk faster. Now, they don't go on the other end because they'd have to go slower than 2 miles per hour, all right? But there's a minimum here for walking to cover a mile. 1.38 calories per kilogram per mile, okay? 0.96, that's if you're 80 kilograms, that's about 80 calories to cover that mile. More calories to cover the same mile, but walking faster. Let's look at running. 3, 4, 5, 6, 7, 8, 9 miles per hour, meters per minute, just different set of units. That cost 1.53, 1.53, 1.53. The same calories used to cover a mile. So it doesn't matter. Again, this is from a textbook. It doesn't matter if I'm running at 3 miles per hour or 9 miles per hour. I'm going to use the same total calories to cover that mile. The rate of calories used is different. Rate of calories used will be analogous to a rate of oxygen consumption. Total calories, a total amount of oxygen consumed. All right, so now I'm actually going to stop there. This is energetic cost of locomotion. And next, I'm going to talk about factors that influence running economy. All right, thank you.